Our next topic is how to measure and measurable sets. So we already stated this problem before. X is a non-empty set, R is a ring on X, and mu is a measure on R. Then we wanted to know if we can extend mu to something bigger. For instance, R is a ring, so in particular it's a collection of subsets. So can we extend mu to S of R? S of R is the smallest sigma ring which contains R. Okay, because we are dealing with measure, countable activity and so on. So it's always better to work with a sigma ring or sigma algebra, because countable unions, countable intersections are close there rather than with a ring. So but to construct something it's easier on a ring, and therefore we want to know if there's some general method to extend it to the whole thing. So for this we have a certain very nice abstract procedure which we will in fact employ when constructing the Lebesgue measure later on. So definition: X non-empty set, S a ring of sigma ring of subsets of X. It is said to be hereditary So the sigma ring is called hereditary if E belongs to S implies F belongs to S for every F contained in E. So if the father has a property, the son's children get it also. So that is the hereditary property. So here, if you have a set E which is in S, then all subsets automatically belong to S. Now of course, power set of X is a hereditary sigma ring. And now if you, as usual, if you take any intersection of hereditary sigma rings, it's automatically hereditary. So it's very easy to check, because we have intersection of sigma rings is a sigma ring, and the hereditary property again, it's very easy to check that it's so. So given E, an arbitrary collection of subsets of X, there exists a smallest hereditary sigma ring containing E. So this is called the hereditary sigma ring generated by E in the usual way we have been talking, and we will call it H of E. Okay, so that is the notation. Now if you take all sets which can be covered by a countable number of sets in E, that means if E is such a set, then E can be written as union EI, I equals 1 to infinity, where EI belongs to E. So this set of all E, so set E can be covered. Okay, so then this is a hereditary sigma. Very easy to check. You can check that it's a sigma ring, it's a hereditary sigma ring, and therefore it should contain H of E. So conclusion is, every element in H of E can be covered by a countable number of elements of E. Okay, so this is an important thing to remember. So now we come to a definition, another definition. So X non-empty set and H a hereditary sigma ring of subsets of X. I am not saying it's generated by anything, it's just a hereditary sigma ring of subsets of X. An extended real valued function mu star on H is called an outer measure. So extended real valued function means it can take infinite values also. 1, mu of E is greater or equal, mu star of E is greater or equal to 0 for every E in H. 2, mu star of phi equal to 0. 3, E in H and F contained in E implies mu star F, because then F is also in H because it's hereditary, is less than or equal to mu star of E. So the monotonicity property is there. And 4, countable subadditivity. EI I equals 1 to infinity in H, then mu star of union I equals 1 to infinity I. It's a sigma ring, so this already in H is less than or equal to sigma I equals 1 to infinity mu star of EI. So this looks like a measure, but there are some differences. First two properties are just the properties of a measure, and then third is a consequence of the properties of measure, which we are now putting in here because that was got from the countable additivity, which we do not have now. And instead of countable additivity, which involved disjoint sets and so on, now we are saying it's subadditive, which is also a property of a measure. Okay, so it is has some properties of a measure, but it's not necessarily a measure. So then an outer measure is called sigma finite if E in H, every E in H can be covered by a countable collection of sets in H with finite outer measure. So E can be written as subset of union EI, and mu star of EI are all finite. So then you call this sigma finite. Just as we had sigma finite measures, we can have sigma finite outer measures. So why are we defining this? Outer measures occur very naturally when we try to extend a measure. Okay, so we have the following proposition. X is a non-empty set and R a ring on X. Okay, and mu is a measure on R. So now you take E in H of R, the smallest hereditary sigma ring containing R. Okay, define mu star of E equals inf of sigma I equals 1 to infinity mu of EI, where E is contained in union I equals 1 to infinity EI and EI is in R. I already remarked that any element of H of E can be covered by a countable number of members of E. So any E in H of R will be covered by a countable number of sets in EI. So you take all possible such coverings, and for each covering you compute this series sigma I equals 1 to infinity of mu I. This could be finite or infinity, and then you take the infimum of this. So this is a very well defined quantity. Then mu star is an outer measure and it extends mu. That means if E is in R, mu star E is same as mu of E. Okay, further, if mu is sigma finite, so is mu star. Okay, so this is the proposition. So the outer measure occurs very naturally from a measure. So given a ring, measure on a ring, you have a hereditary sigma ring generating it, and every element there can be covered by countable number of members of the ring. So you simply take the values of those coverings, so you get infinite series. Now take the infimum of the sums of these infinite series, that is giving you an outer measure, and it extends. Okay, so that's a very important property. So proof. So step 1. So mu star greater or equal to 0 is obvious, because you are taking infimum of non-negative things, and therefore it's non-negatives. Now let us take E belong to R. Then E can be covered by just one element E. Okay, so therefore you have mu star of E is less than or equal to mu of E, because mu star comes from the infimum of all these things. So you have a covering with just one element here, so the series becomes just a single term, which is mu of E, and therefore mu star of E is given by mu of E. Okay, so now on the other hand, if you are given E is covered by union EI, I equals 1 to infinity with EI in R, okay, then what do you know? We know that mu of E by subadditivity of a measure is less than or equal to sigma I equals 1 to infinity mu of EI. So every such sum which you have here is greater than mu of E, and therefore if you take the infimum, so this implies that mu of E is less than or equal to mu star of E. And therefore this implies for all E in R, mu of E and E is the same as, so mu star of E is same as mu of E, that is mu star extends mu. In particular, mu star of phi has to be 0, because phi is the element of E, and therefore its mu star value is same as its mu value, which is given to be 0. Step 2. Suppose F is contained in E, E in H of R. Then of course it's a hereditary sigma ring, so F is also in H of R. So every countable cover from R of E is also a cover for F. So you are taking infimum, so your number of covers for F is more than the number of covers for E, and therefore automatically this implies that mu star of F. When you are taking infimum over a bigger set, the infimum will be smaller, so this is less than equal to mu star of E. Okay, so this proves. So we have proved all the properties except the crucial one. So step 3, we prove countable subadditivity. Okay. So let us take E contained in union EI. I equals 1 to infinity E EI in H of R. So if there exists an I such that mu star of ei is infinite, then clearly mu star of e, whatever its value may be, is less than or equal to sigma j equals 1 to infinity mu star of ej. Okay, because there's one of them, j equals I, which is infinite, so the right hand side is infinity, and therefore this is a trivially true. Okay, so therefore assume mu star of ei is finite for all I. Okay, so now how is mu star defined? It is the infimum. Therefore, given any epsilon positive, there exists eij in R, j equals 1 to infinity, such that eij ei is contained in union j equals 1 to infinity eij, and you have sigma j equals 1 to infinity mu of eij is less than mu star of ei plus some any quantity which I want. I am going to write epsilon by 2 power I. This is just the definition of the infimum. Okay, so you are defining it to be the infimum over all countable covers. So I can find a countable cover which is bounded by mu star e plus any small quantity I like, and I am going to call that quantity epsilon by 2 power I. Okay, then you have E is contained in union I equals 1 to infinity union j equals 1 to infinity eij. So this is a countable cover with eij in R for all ij. Okay, and mu star of E is less than or equal to, therefore sigma I equals 1 to infinity sigma j equals 1 to infinity mu of eij, which is less than or equal to, by our assumption on sigma j equals 1 to infinity, sigma I equals 1 to infinity mu star of ei plus epsilon by 2 power I. Now the second one is nothing but a geometric series which adds up to epsilon, and therefore that is equal to sigma I equals 1 to infinity mu star of ei plus epsilon, and therefore mu star of E is less than or equal to sigma mu star of ei plus epsilon. Epsilon is arbitrarily small, arbitrarily given, and therefore you can send it to 0, and therefore this implies that mu star of E is less than or equal to sigma mu star of ei, which is precisely I equals 1 to infinity, and that proves the countable subadditivity. So step 4, we now take mu is sigma finite. So E is in H of R, so you can write it as ei in R, but then mu is sigma finite, and therefore this is contained in union I equals 1 to infinity union j equals 1 to infinity eij in R, and the measure of mu of eij is finite. So you have a countable cover of E with the eij's, and but mu of ei, mu star of eij is nothing but mu of eij because it's in R, and that of course is less than plus infinity. So E can be covered by a countable number of sets which have finite outer measure. Okay, so this completes the proof of the proposition. So all questions have been proved. So now example. So we said mu sigma finite implies mu star sigma finite. So question is, mu finite, does it imply? It does not imply that mu star is finite, but mu star is still sigma finite because of the previous proposition. Therefore, finiteness doesn't extend, but sigma finiteness exists. So what is the example for this? So let us take n, x to be the natural numbers n, R equals ring of finite subsets. Then of course mu is finite. Mu is counting measure. Countable number union of singletons is in HFR, because HFR is a sigma ring which contains R. Singletons are all in R, therefore any countable n will be singleton. So this implies that n itself belongs to HFR. So, and it's a hereditary sigma ring, so this implies that HFR is nothing but the power set of n. Every subset will all automatically be there. And now if E is an infinite set, clearly mu star of E is plus infinity, because it is, you have to cover it by infinite number of sets, countable number. Each one will have at least measure 1, and therefore sigma mu of EI will always be plus infinity for the infinite set, and therefore the infimum will also be plus infinity. So mu star of E will always be plus infinity. So this implies that mu star is not finite, but it is sigma finite. So we have a very natural way in which given a measure on a ring, there is a hereditary sigma ring and an outer measure. Now given a hereditary sigma ring and an outer measure, we will see how to extract a measure out of it. That will be the thing which we will see next.